Can you hear me at the back if I don't use the microphone?
Yes.
Yes? Great. Okay, thank you all for coming. I'm just going to talk today about a model that I've been working on with Jason Wolfe at the University of Bath, developing this model that can demonstrate evolution of genomic imprinting through adaptation, coadaptation among groups of relatives. So, as I'm sure most of you are aware, genomic imprinting is an epigenetic phenomenon where there is differential expression of alleles at a locus depending on whether they were inherited maternally or paternally. So there is expression of one allele and there may be either complete silencing or only partial expression of the allele inherited from the other parent. How imprinting has evolved, or why imprinting has evolved, is a question that has interested evolutionary biologists for a while now. And there are a number of hypotheses that have been proposed. I'm just going to briefly mention three of these. The dominant hypothesis in the literature is the kinship or conflict hypothesis. This is a kin selection model which recognizes that expression of a gene can have different consequences for inclusive fitness of maternally and paternally inherited alleles. And imprinting may be a way of differentiating expression of the alleles from the different parents in order to maximize their inclusive fitness. The interlocus sexual conflict hypothesis suggests that when there's different selection on the two sexes in a population, there's likely to be different allele frequencies in males and females, and imprinting provides a means by which the allele from the parent of the sex under stronger selection can be expressed. And finally, the maternal offspring coadaptation model suggests that imprinting can increase the phenotypic resemblance of mothers and offspring. And I'm just going to expand a little bit on this last one. So, if there is selection for increased phenotypic matching of mother and offspring, so coadaptation of particular mother-offspring combinations, then this model predicts that there will be maternal expression, I should say, in offspring, because offspring share their maternal allele with their mother, whereas in a randomly mating population, their paternally derived allele is not going to be related to their mother. And so by expressing the maternal allele, they're going to increase their phenotypic matching with their mother. The model doesn't predict evolution of imprinting in the mother, which we do often see, and so there must be other processes that explain this. So the model I'm going to talk about today is essentially an extension of this maternal offspring coadaptation model to look at the potential for coadaptation among wider groups of kin to drive the evolution of imprinting, because interactions with kin beyond just mother and offspring can have consequences for fitness. And one context in which I'm going to talk about this is that of allonursing, which is seen in a lot of mammals, where females form communal nests and nurse offspring that are not their own, possibly alongside their own offspring, so they're nursing all offspring in the nest. This is quite widespread in mammals that form stable social groups. It's well known in rodents, but also occurs in carnivores, primates, even some marine mammals. And importantly, in this context, in most cases where it's been looked at, the nursing females in a communal nest tend to be close relatives of one another. So they may be sisters or mothers and daughters. Okay, so in our model we're interested in asking whether extended coadaptation through interactions with groups of relatives, such as we see in communal nests, can drive the evolution of imprinting. So the assumptions of our model: we're assuming a large deployed randomly mating population, we're assuming a single locus with two alleles, we are assuming that this locus has an additive effect in offspring and also in the nurses with whom they're interacting in the nest, Crucially, the effects we're interested in are, in both cases, effects on offspring fitness. So in the case of the offspring, we're looking at the direct additive effect of the locus on the offspring's own fitness, and in the case of the nurse, the additive effect of the nurse's genotype on fitness of the offspring, presumably mediated through similar trait in the nurse. We assume that the effect of the locus is modified by imprinting with degree I in the offspring, J in the nurses, where these parameters take values between -1 and 1. Negative values imply that there is paternal expression, positive values imply that there is maternal expression. The table down the bottom just gives you, probably the people at the back can't see this, but gives us the expected phenotypic values for offspring and nurses for each of the 4 possible genotypes. Note that there are 4 possible genotypes rather than 3, because with imprinting we need to distinguish between the reciprocal heterozygotes because they're expressing different alleles. And you can see that the effect of imprinting is to, so in both cases, if these values of I and J are positive, the effect is to take the phenotype of the heterozygote towards the phenotype of the homozygote for the maternal allele, and vice versa if it's negative, taking it towards the phenotype of the paternal allele. Sorry, I should say that the maternal allele is the first one mentioned and the paternal allele the second one. Okay, so we're assuming, as I said, that offspring fitness is determined by the offspring's own genotype, by the genotype of nurses with which it's interacting in a communal nest, and by an interaction effect S, which is essentially just the strength of selection on this interaction. And so that gives us a matrix of 16 possible nurse offspring genotype interaction combinations, for which we can estimate a mean offspring fitness for each one. And then the final parameter that we need in this model is an estimate of relatedness of offspring and nurses. And because we're interested in imprinting, we need to distinguish between the relatedness through their maternal allele and their paternal allele. So we've derived these 4 relatedness terms, which explain the likelihood of allele sharing between a pair of alleles in the offspring and the nurse, paying attention to whether we're referring to the maternal allele or the paternal allele. So just as an example, this RMM term is describing the probability that alleles at the maternal allele in the offspring and the maternal allele in the nurse are identical by descent. Okay, so from these parameters we can develop an expression for the mean fitness in the population, which is given by summing the products of the mean offspring fitness for each of the 16 offspring nurse genotype combinations and their frequencies, and we get their frequencies from the allele frequencies in the population and the relatedness terms that I mentioned in the previous slide. And then to look at when imprinting will evolve, we can take these partial derivatives from the mean fitness equation to look at, this is just looking at the change in mean population fitness with respect to a change in the degree of imprinting in offspring and with respect to the change in the degree of imprinting in nurses, to ask when imprinting will evolve in offspring and when it will evolve in nurses. So just to point out a couple of key things we can see from these equations about when imprinting will evolve. Firstly, in both offspring and nurses, we need there to be genetic variation in the population. More interestingly, we see imprinting evolving in both cases when there is an asymmetry in the relatedness of the alleles with the individual with whom they're interacting. So if we just start with the offspring, these terms relate to the relatedness of the maternal allele in the offspring with the maternal allele in the nurse, and the paternal allele in the offspring with the maternal allele in the nurse. So this is essentially saying, if this is not equal to 0, there is a difference in the relatedness of the 2 alleles in the offspring with the maternal allele in the nurse. So we need to see an asymmetry either here or here. Likewise, in the nurses, imprinting will evolve in nurses if there is an asymmetry in the relatedness of their two alleles with a given allele in the offspring. And as far as the direction of imprinting that we expect under these conditions, with the offspring, the allele that they're more likely to share with the nurse will be expressed, and in nurses, the allele they're more likely to be shared with the offspring will be expressed. Okay, so just to bring this back to that context of communal nests and look at what we might expect under a number of scenarios that we can imagine might actually happen. This first column here refers to a number of scenarios about the relatedness of females in communal nests, starting with the simple case where there's just a mother and offspring, no allocare. Mothers are full sibs, females are mothers and daughters, maternal half-sibs, paternal half-sibs, or unrelated. And I've then shown the direction of expression that we expect will evolve in offspring and in nurses under each of these scenarios. So you can see here in the offspring, in all of these situations except the unrelated case, we expect maternal expression in the offspring, and this is because in all of these cases I've chosen cases where the other females are related to the offspring's mother, and so the offspring has always got a higher relatedness through its maternal allele to these females than through its paternal allele. In the nurses, we can see there's a difference. There are some situations where we don't expect imprinting, and then there are these three at the bottom where we do, and the difference in these is explained by this asymmetry in relatedness. So the asymmetry that I've shown here is always referring to their relatedness with the maternal allele in the offspring. They're always related to the offspring through the maternal allele, not the paternal allele, just because of the examples I've used here. And in these first three cases, solitary nesting, which is what we saw with the maternal offspring coadaptation model, but also if the mothers are full sibs, and in certain conditions where they're mother and daughter, there is no relatedness asymmetry here. Here there is, and so this difference in when we see imprinting and when we don't is entirely explained by when there is a relatedness asymmetry or not. Okay, so to conclude, we see that imprinting can evolve through extended coadaptation among kin. It requires an asymmetry between the two alleles in their relatedness with interacting social partners, and they are more likely to share, to express the allele that is more likely to be shared with their interacting partners. This model provides very clear predictions about the relatedness structure that we'll see in social groups for a given imprinted gene, and this may be used to distinguish the mechanism through which imprinting at a gene has evolved from other possible theories of the evolution of imprinting. And I think I'm out of time, so I'll finish there. Thank you.